Linear constrained optimization is a very powerful tool that's capable of solving a wide variety of optimization problems. And specifically, it's able to handle problems with millions of variables, millions of constraints, and solve these problems to global optimality. So the focus of what we're going to be talking about is specifically first starting off with sort of this high level understanding of what is a linear constrained optimization problem. From there, we're going to walk through the actual mathematical formulation of the problem, and then we're going to look at the actual code and start connecting it to the mathematical formulation. And so the goal of this is to build up to the simplex algorithm, which is one method for going about solving these linear constrained optimization problems. So the overall outline of what we're going to be discussing here is, like I just mentioned, we're going to start with this high-level understanding of linear constrained optimization before working up to build the necessary tool set to then construct the actual simplex algorithm. And all of this follows the outline given in the Algorithms for Optimization textbook by Michael Kokendorfer and Tim Wheeler, which is available for free at the following link. So, linear constrained optimization at the high level, all these problems are problems that involve a linear objective and linear constraints. Okay, so when we have a problem with linear objectives, linear constraints, that forms a linear program. So linear program here, just another name for a linear constrained optimization problem. Typically, you'll see them referred to as linear programs. So oftentimes, in the real world though, you have nonlinear objectives and nonlinear constraints. So when that's the case, there's usually a large incentive to try and approximate either your objectives or constraints through a linearization. And the reason for that is what we're going to see later, but essentially we're able to solve these linear constrained optimization problems to global optimality very efficiently. So the overall problem formulation here, there's a few different ways to represent a linear constrained optimization problem. The two that we're going to talk about here, the first one is standard form. So this is where we're minimizing some objective here, in this case C transpose X. This is a linear objective because our variable here is just X, and we're multiplying that by a vector C, which is just a constant. So we have a linear objective. Our constraints here are represented by this A matrix. So A is an m by n matrix in this case, and we have AX less than or equal to B with X greater than or equal to 0. So we call this standard form here. And if we want to get a visual representation of what this looks like, if we look at the gradient of our objective, so the gradient of C transpose X with respect to X is just C. So what we've drawn here is the C vector. We know that the C vector is going to be perpendicular to lines of constant C transpose X. Okay, so this blue line here is showing a line of C transpose X equal to some constant. So anywhere along this line has the same value of C transpose X. The gradient from basic calculus is going to be perpendicular to that line. So if we look at other lines now of constant C transpose X, so other contour lines of our objective, they are also going to be perpendicular to the gradient. So we can look at the same thing now here for a specific inequality constraint. So if we have some vector W here, then this orange line is now going to represent a line of constant W transpose X. So in this case, W transpose X is equal to B, which is some constant. The gradient of this W transpose X with respect to X is similarly going to be W, which is perpendicular to the constraint. So now we can talk about this idea of half spaces. Okay, so a half space is just representing the region on one side of this constraint. So in this case, we have W transpose X less than B forms a half space. You can think about it, it's just basically dividing the space in half. So if we look at now W transpose X greater than B, that's just the other half space formed from this constraint. So that's looking at one specific inequality constraint, but oftentimes we have several inequality constraints. And so when we have several of these inequality constraints, they're going to intersect, and the intersection of these inequality constraints forms our feasible set, which we're denoting by this script X here. And so the cool part about this is that we know that the half spaces themselves are convex sets, and we know that the intersection of convex sets forms a convex set. So this means that our feasible set here that we're working with is also a convex set. Okay, so as a quick refresher of what it means to be a convex set, if we have two sets here, this is set 1, this is set 2, the visual explanation of what it means to be a convex set is pick any 2 points in this set, draw a line between them. If the line connecting those points remains inside the set, then that is a convex set. So in this case, set 1 is a convex set, but set 2 is not a convex set because you can see the line connecting these 2 points leaves the set. Why is this important? Well, in our case, we know that our half spaces are convex sets. We know that the intersection of convex sets is also going to be convex. So all of our inequality constraints, the intersection of those, is going to form a convex set. That means that the feasible set for our problem is a convex set, and we know that our objective, C transpose X, is linear, which is convex. So we have a fully convex problem here. The main takeaway from this is that because our problem is entirely convex, if we find a local minimum, that is also guaranteed to be a global minimum to the problem. Okay, so this is why this is a nice result to have. So talking about these feasible sets, there's 3 different cases of points here that we can consider. Okay, the first is going to be a point on the interior of the set. A point on the interior of the set is never going to be optimal. The reason for this is if we look at the gradient of our objective here. Okay, so if we look at the C vector, again, which is the gradient of our objective, we're interested in minimizing, so we want to move in the negative C direction. So a point on the interior of the set can always be improved by moving along the negative C direction there. And that's why a point on the interior is never going to be optimal. The second case here is when we have points on faces. Points on faces are only going to be optimal if that face is perpendicular to the gradient of our objective. Okay, and just like what we saw before, if that's the case, then we know that that face forms a contour line of our objective. So it's a line of constant C transpose X. This means that if we were to slide our point anywhere along this face, the objective is going to be the same. Okay, so we're not improving the objective by moving along this face at all. And that means here that all of these points on this face are going to be optimal. So there are infinite optimal solutions in this specific case. The third case that we want to consider here is when we have a vertex point. Depending on the orientation of the C vector here, different vertices could be optimal. In this case, the point we've shown here is going to be the optimal solution. Okay, and the reason for that is if we want to move in the negative C direction, then there's nowhere else that we can go. Sort of, this is the farthest point that we can go and still be inside of the feasible set here. Okay, so to get a visual example of what we're talking about here, I think it's helpful to consider this case. Okay, so we're working with our standard form linear program. What we've shown here in this example, you can see the contour lines of the objective here. So these are lines of constant C transpose X. We've shown the negative C vector, and then we're assuming here that there are only 2 inequality constraints. So just these 2 forming this feasible set. We're asking how many solutions are there? In this case, there's only going to be 1 solution. The reason for that is we could just continue to move in this negative C vector direction, and you can see that the furthest down that we can go, the contour lines are decreasing in this direction. The furthest that we can get is this point right here, this vertex point X star. So we just have 1 solution in that case. Now in this case, how many solutions do we have? Well, we're going to have an unbounded solution in this case, because we're assuming that there's only these 2 inequality constraints. So we're going to continue to improve our objective by just continuing to move in this negative C vector direction. Okay, and we'll just be able to continue minimizing the objective out forever, right? We'll just continue to decrease in that direction since there's no constraint stopping us. In this case, this is similar to the case that we just saw. This is where we have points along the face, and that face is parallel to the contour lines and perpendicular to the negative C vector here. So we're going to have infinite solutions. All of these points along this face are going to be optimal. Okay, and then now in this last case here, you can see that the feasible set is empty. So there is no feasible set in this case, and that means there's going to be no solution. Okay, so that's just sort of the visual understanding of what we're talking about here with these feasible sets in standard form. Now, the other problem formulation that we want to talk about is equality form. And linear programs are often solved in equality form. Specifically, the simplex algorithm implementation that we're going to be working with today is using this assumption that we are passing in problems in equality form. Okay, so all we've done to get from standard form to equality form is just replacing those inequality constraints of ax less than or equal to b with equality constraints that ax is equal to b. So how do we actually do this translation between standard form and equality form? Well, if we have some ax less than or equal to b constraints, we can just introduce this idea of slack variables. Okay, so this s variable here is what we call a slack variable, where s is greater than or equal to 0. And basically, we're just saying the same exact thing now. We're just representing that with this s variable. Okay, so we're saying that whatever ax is, we're just going to add on some slack here. So we need ax less than or equal to b. So if we're not exactly equal to b, we're just going to add some slack here, and whatever is left will be made up by our slack variable. Okay, so if we want to see a specific example of this, if we had the problem of minimize x subject to x is greater than or equal to 1. Okay, if we want to convert this into an equality constraint now, what we can do is we're just introducing the slack variable. So we want x to be greater than or equal to 1, so we're going to subtract the slack variable to basically take up the slack on the other side now. Okay, so we just want to subtract s so that we get this hard equality constraint that x minus s is equal to 1. So our problem would then become minimize x subject to x minus s equal to 1, where x and s are now our variables here. Okay, so that's how we would convert between standard form and equality form. So this is just summarizing what we've seen so far with standard form on the left and equality form on the right. Okay, so now that we've seen sort of how to formulate these linear program problems, we want to talk about how do we actually get to this optimality criteria. Okay, and so that's what the first order necessary conditions, also commonly referred to as the KKT conditions, are used for. So we use these first order necessary conditions to determine when a vertex is optimal and to inform how to transition to a more favorable vertex. Okay, so if you recall from general constrained optimization problems, we have this idea of the Lagrangian. The Lagrangian is basically just saying, if you haven't seen this before, what we're saying here is that f of x is our original objective in our problem. This term represents all of the possible inequality constraints that we could have. Okay, and here we're assuming that gi of x is less than or equal to constraints. Okay, so that'll be important here in a second when I make a distinction. So we're assuming these are less than or equal to constraints. These are our Lagrange multipliers for our less than or equal to constraints. And then h here represents our equality constraints. Okay, and the lambdas are for the equality constraints. So if we want to write the Lagrangian for our specific problem, that's going to look like the following. So we have our problem now in equality form, and we want to write the Lagrangian. Recall just what the Lagrangian is saying. It's taking our original objective, and we're just penalizing here deviations from these constraints. So if we're not satisfying these constraints, we want to be able to penalize that through these Lagrange multiplier terms. Okay, that's the whole idea behind the Lagrangian here. So in our specific problem now, we have the Lagrangian here would be our objective. So our f of x here is just c transpose x. That's our objective. Now notice that we are subtracting mu transpose x. Why do we have a minus sign when up here we had a positive sign, right? The answer to this is because we assume that these gi of x were less than or equal to constraints. Here we have x greater than or equal to 0. So in order to get this into this form, we need to flip the sign here, right? When we flip the sign, that flips the inequality. So that's why we have this negative mu transpose x term, okay? For the equality constraints, the sign of lambda actually doesn't matter. So we do have a constraint on the sign of mu here, but for lambda, it doesn't matter. And you'll see why here in a second when we talk about the primal problem. But we can define this to be plus or minus either way. And then when we actually solve the optimization problem, the specific Lagrange multipliers that we get here for the equality constraint will make up for that. Okay? So that's the Lagrangian for our specific linear constrained optimization problem. Now if we want to look at the first order necessary conditions here. There's 4 different first order necessary conditions. The first one is just feasibility. All this is saying, I think this is the most straightforward one, is just saying that in order for us to be optimal, we have to satisfy the constraints, right? The original constraints of the problem, if we don't satisfy those, then there's no way that we could be optimal. Okay, so that's all this is saying. We have to satisfy the original constraints. The second one is dual feasibility. This requires that mu is greater than or equal to 0. I found that often this condition is typically neglected in people's intuition of why we require mu greater than or equal to 0. I think the best way to sort of keep this straight is through this visual example, okay? What we're trying to do with the Lagrangian is we're trying to penalize infeasible points, right? We want our points to be feasible, so we want to penalize any points that are infeasible. So for this specific constraint, let's say we have this x greater than or equal to 0 constraint, which we do. If we want to look at the penalty that we would like to apply here, that's what we're going to show on this axis. Okay, so for x greater than or equal to 0, we're saying we don't want to apply any penalty. This is just 0 penalty that we're giving because it's a feasible point. As soon as we're slightly less than 0, we want to apply infinite penalty, right? That point is infinitely bad to us since it's not feasible. Okay, so that's what we're saying here with this infinite step function. The issue with this is that this is not very conducive to optimizing, right? Because we have this discontinuous step function here. There's no gradient information here. So what we do instead is we say, okay, let's use this linear penalty here, which is just represented by our mu transpose x, and we're saying let's apply this linear penalty now for any infeasible points, okay? And this is why we require dual feasibility. Dual feasibility is saying that mu has to be greater than or equal to 0, which means that the slope of this line needs to basically point in this direction. We have to have the linear penalty going in this direction. If instead we were to run sort of into the positive quadrant up here, that would not make sense with this infinite step penalty that we're trying to apply. Okay, so that's why we require dual feasibility, because mu is related to the slope of this penalty that we're applying. And we'll see here this picture again for this next first order necessary condition, which is complementary slackness. Okay, complementary slackness here is represented by this element-wise multiplication. So this is just saying that either the component of mu or the component of x is going to be equal to 0. Why is this the case? Well, we can look at this picture again to sort of get the intuition here. Looking specifically at this mu transpose x term, since we're trying to recover this infinite step penalty, instead of just using the infinite step penalty, we've introduced this linear term here, this linear penalty term through our Lagrange multiplier. Now we're saying, okay, let's maximize the penalty that we receive subject to mu greater than or equal to 0. So this means mu is the variable that we're controlling here. So what this looks like, okay, if we have the case where x is less than 0, we're going to be over on this side. What happens now is we're trying to maximize the penalty that this infeasible point receives. Our control that we have over this is our parameter, this mu here, our Lagrange multiplier. So we're basically just going to crank mu up as high as possible so that we can get the maximum penalty here. And that's exactly what we do. You see, we crank mu up and we actually recover this infinite step penalty now. So now we can look at another case here, okay, in the case that x is greater than 0, we're on this side over here. Now what's going to happen? Well, look, when we're at this point, the penalty that we're receiving right now is actually a negative penalty. But we want to maximize the penalty that we receive. So in order to do that, we're going to change mu, right? Mu is the variable here in this maximization. So we're going to vary our mu here to increase the penalty that we receive, but the largest penalty that we can receive in this case is 0. We can't go any higher due to the constraints on mu. And this makes sense, right? We are feasible at the moment, so we don't want to penalize at all. Our point is already feasible, so we shouldn't be penalizing this point. Okay, and then the last case that we consider is when x is equal to 0. When x is equal to 0, well, we're also going to receive no penalty there. But notice now that the constraint here is actually active. So we have an active constraint since we're right up against this greater than or equal to constraint. at this point. And so that's all complementary slackness is saying, is that either the constraint is going to be active or inactive. All right, either mu or x is going to be 0. That's what complementary slackness is telling us. The last first order necessary condition that we have here is stationarity. And now notice what we've done. We've rewritten this. So this was our infinite step penalty, right, that we introduced here through our Lagrange multipliers. Now we've put that back into our original objective, which is to minimize with respect to x. Okay, and so this is what's called the primal problem. And so stationarity here says that A transpose lambda plus mu is equal to C. Where does this come from? Well, this comes from the fact that at an optimal point, right, we need to have the gradient with respect to x of our Lagrangian has to be equal to 0 because we're trying to minimize this, so we need this condition to hold. Another way to think about this is that this is saying that the objective function contour is tangent to each active constraint. That's another way to look at this. Those are the first order necessary conditions, and it turns out that for linear programs, the first order necessary conditions are actually sufficient as well. What this means is that in a general constrained optimization problem, the first order necessary conditions are necessary, meaning that if you just have some point x and it satisfies the first order necessary conditions, it doesn't necessarily mean that that point is optimal. Okay, so it's not sufficient in the general case to show that that point is optimal. However, if you're working with a linear program and you have a point x that satisfies the first order necessary conditions, then you know that that is the global optimal solution. Okay, so that's what it means to be necessary and sufficient here. Why is that the case, right? That's not just immediately obvious and why this is. So the intuition here is that the gradient of our objective is constant at any point that we consider in the space, right? We know that the gradient of the objective is only going to point in one direction. And like what we saw before, we know that our problem is entirely convex. Okay, so this means that any local minimum we find is also going to be a global minimum. Okay, that's why this is a powerful result here. If you're interested in all of the details or in additional information on this specific point, I'll refer you to section 5.2.3, which discusses Slater's condition, and 5.5.3, which discusses the KKT conditions in Boyd and Vandenberg. Okay, so what we're interested in now is building up to the simplex algorithm. And this is sort of the tools that we will need to get there. What we've seen so far is first order necessary conditions, the idea of this feasible set, and overall equality form. What we're still missing as the tool in our toolkit to get there is this idea of vertex partitions. For our linear programs, every vertex for a linear program in equality form is going to be uniquely defined by n minus m components of x equal to 0. When you see this just written up here, I think you might be like, okay, I don't really understand why that is, right? So I think it's best to see this through an example. So here, consider this fairly simple example where we have minimize x1 subject to x1 plus x2 equal to 1. Okay, and then we also have x greater than or equal to 0. So we're in equality form right now. So the visual representation of this, what this looks like here, if we have x1 and x2, the constraint here, x1 plus x2 equals 1, is just this line, all right? Now, the vertex points that we're going to have here, one of them is going to lie at this point, which is just 0, 1. Notice that the first component is 0. The second vertex point we're going to have is at this point, okay? And notice here that the second component is 0. So in this case, we have n equal to 2 because we have two variables here, x1 and x2. M is equal to 1 because we have one equality constraint, x1 plus x2 equal to 1. So n minus m is 1. Okay, and what we saw was that each vertex is going to be defined by n minus m, or one component of x that is equal to 0. And that's exactly what we see. Now, this is a nice, just simple two-dimensional example, but the problems that we're going to be working with often have many more variables than this, thousands up to millions of variables. So we're not going to be able to draw out these nice pictures to get this visual intuition. And as a result of that, I think it's better to keep in mind the linear algebra interpretation because that's a little bit more extensible to the problems that we're actually interested in. So we're going to look at the exact same thing here, now just from a linear algebra perspective. what we're saying here, we have 5 variables now. We have 3 equality constraints represented by the rows of our A matrix. So now if we carry out this AX equal to B matrix multiplication here, we're just basically going to look at what happens when some components of X are equal to 0. Okay, so in this case, let's say that we have X2 and X5 are 0. So when we go through this matrix multiplication, we're going to multiply the first row of A times the vector X, and you'll notice that the second and fifth components of A will just be zeroed out because of the zeros here. So what ends up happening is that the entire second column and the entire fifth column of A don't actually contribute anything because they're just going to be multiplied by zeros. As a result, we can rewrite this matrix multiplication just in terms of the first, third, and fourth columns of A. Similarly, the first, third, and fourth components of X. And so what we've done here, recall that we had n equal to 5, m equal to 3, so n minus m was 2. We set 2 components of X equal to 0. Okay, so what we're building up to is this same idea, but looking at the linear algebra interpretation. Okay, so in the case that this A matrix that we're left with is invertible, so if this is an invertible matrix, then we are going to have a unique solution to this problem. How do we do that? How do we see this? That's what we're going to look at next. So keeping in mind this linear algebra interpretation, we're just going to extend this now and introduce the idea of partitions. We have this variable X that we're working with, this vector X. There's n components here. So this set here that we're showing is representing the indices of X. Okay, so we have n components of X. So 1 represents the first component up to n represents the nth component. We're going to introduce 2 sets here. So this set we're going to call the basis set, and this set we're going to call the free set. What this means here is that if we have an index in the basis set, then the ith component of X is going to be greater than or equal to 0. Okay, that's what it means to be in the basis set. If you're in the free set, then for any index I in the free set, xi by definition is equal to 0. So in the basis set, we're going to have m elements. In the free set, we're going to have n minus m elements. Okay, and this is relating to what we saw before, that n minus m components of X equal to 0 are going to define that vertex. So if we look at the example that we just saw with the X vector here, in this case, our basis would be the indices 1, 3, and 4, and our free variables here would be the indices 2 and 5. So another way that I like to sort of keep this straight is B stands for busy here. So if you're in the basis set, you're busy. And if you're in the free set, you're vacant or you're 0. So busy and vacant, or basis and free. 2 ways to think about it. Extending this now back to the linear algebra interpretation is what we were talking about. We know that if you're in the free set, then the X components are 0. So we have these constraints that AX is equal to B. Well, we can just rewrite this in terms of A basis and X basis. What are A basis and X basis? Well, that's what we just saw, right? This is the AX term here. And then A basis is just the 1, 3, and 4th column of A. Similarly, X basis is just the first, third, and fourth component of X. So we can just rewrite it in terms of the basis, and then we can solve for X basis. Now, this is exactly what I was saying before. If A basis is invertible, meaning A basis is full rank, then this is going to have a unique solution. And we know that X basis will be greater than or equal to 0. So the important thing to keep in mind here is that while every vertex has an associated partition, not every partition corresponds to a vertex. So I think the best way to see this is through an example. So consider the case here where we have the following AX equal to B constraint. And imagine someone comes up to you and says, okay, hey, the basis here is 1 and 2. And you might be like, well, I don't really believe you that the basis is 1 and 2. So you could check and say, okay, let's look at A basis times X basis. All right, so the basis here is 1, 2. So that means A basis is made up of the first and second column of A. Okay, so we build A basis, X basis, but now we can see right away, okay, this A matrix here is not invertible. It's not invertible because it's not full rank, right? So we're not going to get a unique solution to this problem. So just because someone gives you a partition does not necessarily mean that that partition corresponds to a vertex. Okay, so every vertex will have a unique partition, but not every partition will correspond to a vertex. All right, that's an important thing to keep in mind. It's not a two-way street, it's a one-way street. Now, like I mentioned at the beginning, we want to start building up this code that we'll actually use to connect to the mathematical formulation, and then eventually we will use to build the entire simplex algorithm. So we're implementing this in Julia, but the implementation is very high level, so it's easily translated to Python or any other language that you want to use. So we're going to start off here by creating this mutable struct to store our linear program. Okay, so that's just going to take our A matrix and our B and C vectors, and that's all we're storing in our linear program struct. So we're going to introduce this function, getVertex, which takes in a basis. You can think this is just a list of integers here that we're taking in, and it also takes in our linear program. Okay, so the first thing that we're going to do is we're just going to read in the A, B, and C values here from our linear program that we pass in. We are then going to sort the indices that are passed in the basis, because it's not necessarily the case that the basis indices will have already been sorted. So we're going to sort them here, and then we're going to access the columns of A corresponding to those basis indices. Now we saw that we can solve for X basis by just taking the inverse of A basis multiplied by B here. So that's all we're doing in this line. And then we're going to initialize the X vector here to be n zeros. So remember, we have n components. C is going to be length n, so we have n zeros here. And then we're just going to set the components corresponding to the basis indices to be equal to X basis, and we'll return X. So what we've done in this getVertex function is literally just that. We take in a partition, a linear program, and we return the vertex. And we'll continue to build on this code that we're sort of introducing here as we work up to the entire implementation of the simplex algorithm. Okay, so now we've seen all of the necessary tools that we'll need in order to construct the simplex algorithm. So we have all of the tools in our toolkit. Now we just need to go through some of the details of the specifics in the simplex algorithm. So the simplex algorithm is guaranteed to solve any feasible and bounded linear program. The way it does this is by essentially moving between the vertices in our feasible set here until it finds an optimal vertex. So at each new vertex, it's going to check the first order necessary conditions. If it satisfies the first order necessary conditions, then we know that that is an optimal point, as we've seen before. If it doesn't, then we're going to transition to a new vertex. How we do that transition is going to be the focus of this part. Okay, so the simplex algorithm has two phases, the initialization phase and the optimization phase. The initialization is focused on first finding a starting vertex. So we need to find a feasible starting vertex. And then phase 2 is focused on finding the optimal vertex. So we're actually going to start with phase 2 because that's where the bulk of this algorithm takes place. Then we're going to come back to talk about phase 1 and how do we actually initialize this with a feasible starting vertex. Okay, so the optimization phase. In the optimization phase, we're focused on this transition between x and x prime. And we know that this transition has to satisfy ax prime equal to b. We're assuming here that we're starting with some initial partition. Okay, in phase 1, we're actually going to solve for this, but for now, we're assuming we have some initial partition to work with. The optimization phase boils down to simply just choosing an entering index, q, from our free variables, and a leaving index p from the basis. That's all that's going on here. How we actually choose this is going to be determined going back to the foundation here, which is the first order necessary conditions. Okay, so we're interested in making this transition. What we're first going to do is just rewrite the first order necessary conditions in terms of our partition. All right, so first looking here at stationarity, we can just rewrite this stationarity condition in terms of the basis and free indices. We've just rewritten the same exact thing here, but now just indexing into our A and our mu components in C. Now we can notice from complementary slackness that we have mu of our basis equal to 0, right? Because either mu or x is going to be 0. So what this allows us to do is then solve for lambda, okay? Because we know from this equation here that mu of our basis is 0, so this allows us to solve for lambda as A basis inverse transpose C basis. So this is good because now it allows us to actually compute our Lagrange multipliers, which will allow us to check the first order necessary conditions given some partition. Okay, so this is good. But what we're still focused on, we want to make this transition, right? We want to transition between x and x prime. In this transition, we're going to talk about this point that we're going to call x basis prime, okay? And we'll break down what this means here. So this transition, we're just going from x to x prime here, and assume that at this x point, our basis is 1, 2, okay? So what x basis prime here means is let's look at x prime now, but use the old basis that corresponded to our x point, okay? So we're looking at x prime using that old basis that we had for the previous point, okay? So if we look at x basis prime now, corresponding to this basis here, it would be x prime 1, x prime 2. Okay, that's what x basis prime means. Looking at the new point, but with the old basis. So what we know here, remember, we're trying to find the entering index Q and the leaving index P. So the leaving index, by definition, will be 0. The value has to be 0. So this is saying x prime basis, so the new point using the old partition, has to have the pth component equal to 0. That's what it means to be a leaving index, okay? So we have the leaving index P, the one that is leaving the basis. We know that the x prime basis, the pth component of that has to be 0, all right? That's what this is saying. We can now rewrite the constraints that we have. We know that we have to satisfy ax equal to b, and we also have to satisfy ax prime equal to b. So at this new vertex point, we still need to satisfy this constraint. We saw before that we can just rewrite this as a basis x basis equal to b. So now what we want to do is write this constraint in terms of our x basis prime point. Okay, so to do that, we just simply have this expression. What this is saying here is that ax prime is equal to a basis x basis prime, where remember, one component here is going to be 0 because it includes the leaving index that is left. Okay, so one of these is going to be 0. So this term is accounting for what is leaving the basis. Now we also need to include what is entering the basis. Recall that Q is the entering index. So Q is coming from our free variables, and now we have to include that because it's entering. So this is sort of just like a mass conservation here, right? You can think about it like that. We have what's leaving the system and then what's entering the system. Okay, that's all we're doing here. And that is equal to ax prime. So now we can just simply rewrite this and solve for x basis prime. Okay, so just taking these two lines here and solving for x basis prime, we end up with the following. And now what you'll notice here is, while this is nice that we've been able to sort of write this explicitly in terms of x basis prime, we still don't know xq prime. Okay, so that's still something that we need to find. And that's what we're going to be focused on next. So how do we find this xq prime? Okay, so just like we rewrote the constraint above in terms of x basis prime, we're now going to rewrite our objective in terms of x basis prime. So this is saying the objective at the new point that we're going to be looking at, just like what we did above, is just C transpose basis, x basis prime. So this is accounting for what is leaving the basis. And now we also have to account for what is entering the basis. So this is what's the new contribution to our objective is. Just the same exact thing we did above. And now we can make some simplifications here because we've solved for x basis prime. So we can now plug this in to this expression. And what we end up with is now going to be this term here. So all we've done is just plug in x basis prime. And now we can make some simplification. Okay, so just distributing the C basis transpose here, we end up with this term. But now notice that this C basis transpose A basis inverse, well, that's just lambda transpose, right? Because we saw from before that lambda was equal to A basis inverse transpose C basis. So this term here is just lambda transpose. Okay, so we can substitute that in now. And all we've done is include here lambda transpose. Now we have one more substitution that we can make here. Recall from what we saw before with writing the first order necessary conditions in terms of our partition. We saw that we had this expression for the stationarity condition. And notice that this is in terms of all of the free variables. But if we want to write this just in terms of one of the free variables, in this case q, so the qth index here, we just have this expression here for A transpose q, so the qth column of A times lambda equals cq minus mu q. Okay, and then notice here that this is just a scalar term, so the order of this transpose doesn't actually matter here. So this lambda transpose AQ up top is actually equivalent to just CQ minus mu Q. So now we can substitute that in as well, and what we end up with is this expression. So now we can just make some simple simplifications here. We're just distributing the xq prime, and notice that these two terms will now cancel out, so we are just left with now C transpose X plus mu Q xq prime. Where does this C transpose X come from? Well, remember, C basis transpose X basis is just another way to write C transpose X. Okay, so that's all we've done. So the final result that we end up with from going on this journey here is that C transpose X prime is equal to C transpose X plus mu Q xq prime. We can just bring the C transpose X over to the other side and we get this. Okay, why is this a useful result? Why is this important? Well, notice what this is telling us. This tells us the objective function here, when we move from x to x prime, is only going to decrease if this mu q term is negative. Okay, so what that means is that in order to progress toward optimality, we want to be decreasing our objective, right? So in order to do that, we need to choose an index from our free variables such that mu q is negative. If, however, all of the components of our mu Lagrange multiplier, so if all of the components in the free Lagrange multiplier indices are non-negative, then that means we found a global optimum by dual feasibility, okay? So this is why this is a useful objective, because we can use this to sort of inform first what Q index is going to enter, and then assess at the same time, are we progressing towards optimality? How do we actually use this, right? This gives us some guidance, but it doesn't tell us exactly what Q index to pick. So in order to do this, we first are going to choose the entering index. Remember, we're first choosing the entering index Q, and then we're solving for the leaving index P. The question now is, how are we choosing the entering index? And so there's a few different entering heuristics. What we're going to be using in our implementation in this example is the greedy heuristic. So this is just choosing the Q index that maximally reduces our objective. Okay, there's other entering heuristics out there as well. You can also use a combination. This is not an exhaustive list here, so you can use a combination of these. There's many different variations, and these are just to be aware of that these entering heuristics exist. To keep it simple, we're just going to use the greedy heuristic in our implementation today. We first choose an entering index, Q. We're choosing that based on the Q that maximally reduces our objective. Once we've chosen that Q, we're then going to solve for the leaving index P. How do we solve for the leaving index P? That's sort of the question that we have now. So this is the expression we saw for x basis prime before. And recall, we saw that the pth component of this has to equal 0, since that is our leaving index. That's the index leaving the basis. So we can just rewrite this top expression now using this fact in terms of the pth component here for each of these terms. And now this allows us to solve for xq prime. Okay, so if we just rearrange this now for xq prime, what we have is this expression. Okay, and this is typically referred to as the minimum ratio test. Why the minimum ratio test? What does this mean? Okay, this is saying that essentially we want to increase xq prime. We want to increase xq prime up until one of these components, specifically the pth component, becomes 0. Okay, so we start increasing xq prime and we want to take the minimum ratio here. So the minimum value of xq prime that causes this to become 0. That's what we're interested in. Okay, the reason for that, when xq prime is 0, right, this is just a strict equality here between x basis prime and x basis. As we start increasing xq prime, then as soon as one of these components becomes 0, that's the first one that we want to take. Okay, that's why we're interested in the minimum ratio. Okay, so this is solving for that specific xq prime. Now, how does this actually work? Essentially, all we're going to have is a nested for loop, right? That's one way to think about this. In the outer for loop, we're going to go for all of the q in our free indices. Then we're going to look at for all of the p in our basis. And what we're trying to do here is we're trying to find a QP pair. So we're going to look at each QP pair. So starting with the q in the outer for loop, we're going to go into the inner for loop, look at each p in the basis. For each of those p's, we're going to compute this minimum ratio. So we're going to first find the minimum ratio. And then we're going to check the greedy heuristic, which tells us how much is our objective decreasing by. We want to select the xq prime, so the pq pair, corresponding to the greatest decrement in that objective. Okay, that's sort of just the initial portion of how this is going to work. We're going to see a full example of actually what this for loop really looks like, but this is just sort of to get you thinking about how is this process going to work. So now for the example here. Again, we're working with the equality form, and let's consider the case where we have the following a, b, and c values. Additionally, let's assume that we're given some basis here, 3, 4. In phase 1, remember, we're actually going to have to solve for this basis ourselves. For now, we're assuming it's given to us. We're going to actually go through phase 2 of the simplex algorithm now. So it's going to start with this minimize LP function. In Julia, this exclamation mark denotes that we are modifying the arguments that are passed into the function. Okay, so in this case, we're modifying the basis here, and that's what the exclamation mark denotes. The minimize LP function, we enter into it, we just initialize done to be false, and then we're going to continue to call this step LP function until done is equal to true. And this is just indicating whether or not we found the global optimum. So we're going to continue to call step LP until we have found the global optimum. So let's actually go into step LP now. Okay, so this is the step LP function here. What we've done to initialize, right, this is just sort of straightforward, what we've already seen. We sort our basis indices, and then now the free indices here, these n indices, we're just saying it's the set difference. So the set difference between 1 through n components and what's in our basis. So just basically all we're saying here is take whatever components in 1 to n that are not inside of our basis and then sort them. Okay? We extract the columns of A corresponding to the basis and the free, and then we solve for x basis here. Okay, so to solve for x basis, notice A basis is just the third and fourth columns of A here. We're taking the inverse of that and then multiplying by B. So we just get 9, 2 for x basis. Similarly, just take the third and fourth components of C. That's our C basis. And then remember, we can solve for our Lagrange multipliers here. So lambda is just A basis inverse transpose. We saw A basis was just the identity here. C basis is 0, 0, so we get lambda equal to 0, 0. And recall this came from what we saw previously for these equations, that lambda was equal to A basis inverse transpose, and we had this expression for the free mu's. So we can similarly compute mu for the free. Notice we have the first and second components of C now, so this 3, negative 1. We have the first and second columns of A here, and then just the lambdas that we just solved for. Okay, and that gives us 3, negative 1. Now we are ready to go into that outer for loop that I was talking about. Okay, so we're going to iterate now for each of the free indices. We're going to go through each of the free indices in this loop. Okay, and what we're trying to do here is we're trying to find the maximum decrement in our objective. Which Q value is going to give us that maximum decrement? That's what this for loop is focused on. So we're going to go in here. We're going to check, is the first component of mu v, is that less than 0? Why are we checking if mu vi is less than 0 here? Well, remember, we want to decrease our objective. That only happens if mu q in this expression is negative. So that's why we're checking here. We only care about negative mu q's. We don't care about positive mu q's. Okay, so in this case, where mu vi is 3, it's not less than 0, so we're going to skip this. We're going to come down to the end of this if statement and then go back up to the top of the for loop. Okay, so now we're on the next component of mu v, which is negative 1. Here, mu vi is less than 0. It's negative 1. So we're going to come in here And now we're looking for the PQ pair, right? So we want to solve that minimum ratio problem here to find that the minimum ratio, which will give us that XQ prime value as well as the P value. Okay, so we're going to do this inside of this edge transition function. Okay, so we're going to save our spot here. We're going to enter into the edge transition function. And now we are inside the edge transition function. Notice that the values that we've passed in here, we have our 3, 4 basis. We have Q equal to 2, because that was the iteration we were in that outer for loop, was for the second index, the second free index. So Q is 2 and N is 2 here that we just solved for in the size of A. Just like before, we're going to get our basis and free indices. We're going to extract the columns of A. And now this D term stands for denominator. Okay, so we're going to solve for this denominator term here. So we have our A basis here, which we saw was just the identity. Then we're taking the inverse of that. And now AQ here, notice what we have in the code is Q is 2. So in our N indices, the second component of our N indices is 2. So we're taking the second column of A up here. So the second column of A is just 1, 2. And then we are plugging that in to this expression. So what we end up with here is just 1, 2. So that's our denominator term. But we haven't taken the pth component yet. Okay, that's what we're going to do inside this for loop. So inside this for loop, we're interested in finding this minimum ratio XQ prime here. So we're going to iterate through each component of D here. Inside, we're going to check, is D greater than 0? Why do we care if it's greater than 0? Well, because we're going to be dividing by it, so we don't want to divide by 0 here. Okay, so we are going to compute the value here. The value is just XBI, so in this case, the first component of X basis, which is 9, as we saw up here. So 9 divided by the first component of the D vector, which is just 1. So 9 divided by 1 is 9. We then check, is that value less than the best XQ prime we've seen so far? Well, it was initialized to infinity, so yes, it is less than that. We're going to store that P XQ prime pair now as what we've currently seen. Okay, so P is 1, the corresponding index, and the value is 9. We're then going to continue in this for loop now for the next step. So now we're looking at the second component of D. Is that greater than 0? Yes, it is. Let's compute the value for it, which is now the second component of X basis, which is 2, divided by the second component of D, which is also 2. So our value is 1. Now, is the value less than the best XQ prime we've seen so far? Well, the best XQ prime we saw so far was 9. So yes, it is less than that. And we update our P XQ prime pair. Now we finish this for loop, so we're going to return the current P XQ prime pair that we found. And this is the minimum XQ prime. Additionally, we're also returning the P that corresponded to that minimum ratio. This finishes our edge transition function. Now we can return back to our step LP function, and we'll return the P XQ prime pair that we found. Now, with this P XQ prime pair that we just found in the edge transition, we're going to go and compute the decrement in our objective. Okay, so what is the decrement in our objective? It's going to be the component of mu vi, so this is -1, that's where we left off here, times the xi prime that we just found, which was 1, that we just returned from edge transition. We're going to check, is that less than delta? Delta is the best decrement that we've seen so far in our objective, which we initialized to infinity, so yes, it is less than that. We're then going to now store the PQ pair. So this represents the swap that we're trying to achieve, right? This is the Q, the entering index, P, the leaving index, and the corresponding XQ prime. So we update those values accordingly. And now we've actually finished this for loop. Okay, so we're done here. And now we're just going to go into some optimality checking. First, we check, is Q equal to 0? Well, why do we check if Q is equal to 0? Well, notice what this means. We initialize Q to 0. So if Q is 0 after going through this for loop, that means that we never found mu vi less than 0, okay? Because we never ran any edge transitions, we never made any updates to Q. So this means that all of the components of mu are going to be greater than 0, in which case we satisfy dual feasibility, and we know that we've reached the global optimum point, okay? So we're going to return the basis and true, indicating that, hey, we found the optimal point here. That's not the case for us, so we're going to continue on to the next check here, which is saying, is XQ prime infinity? for us, this is also not the case, but what would this mean? Well, this would mean that we made it through, so Q is not 0, meaning that some swap did occur here, but XQ prime was still infinity after this, okay? So meaning that in our edge transition or somewhere else, XQ prime has continued to increase to infinity. And that is telling us that this problem is unbounded, there's an issue here, okay? And so we would return an error. That's not the case for us, so we're gonna move on to this line here. And what this is doing is basically just finding the first component that is equal to, so B indices of P, so that's the second component of our B indices, which is 4. So now we're just finding the first component of B that is equal to 4. Well, that's just the second component. So why is this line necessary? Well, this is just for the fact that we sorted B, remember? So we sort B, and so this is just sort of re-indexing back in to sort of correct for the sorting that we did to start. Okay, and then this is where the swap is actually occurring. So now we're setting the second component of the basis. So we're switching this 4 now. The 4 becomes a 2 because n indices of Q is 2. So we substitute that in to our basis. Our updated basis is now 3, 2. So then we're going to return the updated basis and false since this is not the optimal point yet. Okay, so we're going to return back to the minimize LP function, and what we returned was 3, 2 and done equal to false. Okay, so that was one iteration of this step LP function. We would then now repeat this in this while loop since we haven't reached done equal to true yet. We're not actually going to do that here, but you're welcome to try it out on your own. It would only take one more iteration here to converge to the optimum, and the result that you would find in this next iteration, you would see that all of the components of mu are positive, which means that we satisfy dual feasibility, and this is the globally optimal point, okay? And the optimal partition there would be 2, 3, with x star, the optimal point, given here. Okay, so you're welcome to try that out on your own and see if you get the same thing to sort of test your understanding of working through this code that we've developed. Okay, so the functions that we've seen so far, we've seen the first 4 functions here, and that is the entire phase 2 of the simplex algorithm. So I think that's just pretty cool that in roughly like 100 lines of code here, we've been able to write the entire phase 2, the optimization phase of the simplex algorithm. And this is capable of solving just extremely large linear programs, and it can all be concisely written by this small portion of code. So I just think that is really a beautiful thing that you have this much power in such a small portion of code here. So the last part of the simplex algorithm that we're going to implement is just this minimize LP function. Okay, and so this is going to incorporate both phase 1 and phase 2 now. So just recall that what we've seen is only phase 2, right? And phase 2 is focused on finding the optimal vertex, which is really the bulk of the work here. Now we need to talk about how do we find a feasible starting vertex, okay? And that's phase 1 of the algorithm. So as it turns out, identifying partitions that correspond to vertices actually involves solving a linear program. And so when you see this, you might be like, wait, you're telling me that in order to solve a linear program, I first need to solve a linear program? Isn't that just a circular loop and I'll never actually be able to solve it? Well, no, that's not the case. We can actually solve these linear programs, and we'll see how in a second here. So our goal is to find an initial partition that corresponds to a vertex. Okay, so in order to do that, we're going to introduce this following auxiliary linear program, okay, where we introduce these z variables. You'll notice what we have here, our objective is basically to minimize the z variables. So if we do everything correct here, then the ending z's that we get should be 0. Okay, so the goal is to zero out these z variables. The constraints that we have are just like before, where we have this ax plus z matrix now, so zz equal to b. And we also require x and z greater than or equal to 0. Okay, so this is our auxiliary linear program. This is not equivalent to the actual problem we want to solve. This is just the linear program we're introducing in order to find the initial partition. So what is this z matrix here? The z matrix is a diagonal matrix. So along the diagonal z here, the component is going to be positive 1 if the corresponding bi is greater than or equal to 0, and negative 1 otherwise. Okay, so when you see this now all written out like this, I think it's kind of common to be like, okay, I don't really see how this is helping us at all. And you might have two questions here. The first question would be, well, don't we still have the problem of finding an initial partition to solve this problem? And the second question might be, why are we defining this Z matrix like this? So we can answer both of these questions. Let's start with the second question first. Why is Z defined like this? So if we write out this constraint, this is just AX plus ZZ equal to B. Okay, so consider the case here where X equals 0. If X is equal to 0, then we just have ZZ equal to B. Now remember that we have constrained Z to be greater than or equal to 0. B, however, can have negative components. So in order for this equality to hold, we need another degree of freedom available to Z. And that's why we introduced this Z matrix that has negative components in it, to give Z that freedom in order to make this equality exact. Okay, so if Z is greater than or equal to 0, we need some way to make this equality hold if B is negative. And that's where our Z matrix comes in. Okay, so that answers the second question of why is Z defined that way. Now we still have this first question. Don't we have the problem of finding an initial partition? How do we know an initial partition to solve this problem? Well, if we look at this auxiliary vector here, xz, then if we just kind of write everything out, what we'll have is n components of x and m components of z. But notice here that if x is equal to 0, what we have is just n zeros stacked on top of the mz's. And this, it turns out, is actually a valid initial partition to this auxiliary linear program. Okay, so the partition here would be the indices n plus 1, corresponding to the first z, up to n plus m, which is the last z here. We would also initialize zj equal to the absolute value of bj. Why is this a valid partition? Well, notice it satisfies our constraints. Okay, so we have ax, which is just 0. So what we actually have is just zz is equal to b, which is true since the way that we've initialized it here. And we also have that z and x are greater than or equal to 0. So this is a feasible initial partition. We can now do this for any of these auxiliary linear programs. We're always going to have this initial partition, this valid initial partition for this auxiliary linear program. Okay, so we've answered both of those questions now. Now, when we go and solve this, the optimal value that we get for this auxiliary linear program should have all of the z's zeroed out. So seeing this in words, what this is saying is that the partition obtained by solving that auxiliary linear program will produce a feasible design point, meaning ax will equal to b, because z will have been zeroed out. So we'll get a feasible design point by solving that auxiliary linear program because the z's will have been zeroed out. But if z is non-zero, that means that the original linear program is infeasible. And so this sort of tells us, hey, we can stop right here. We don't have to go any further. We know that the original linear program is infeasible. So I think it helps now to sort of see this whole pipeline of this initialization phase written out. So first, what we're writing here is the new form of the problem. Okay, this is still equivalent to the original form of the problem that we had with this objective and our constraints, but now we're leaving in the z's. Okay, so we still have the objective of C transpose X. We still have AX is equal to B, and we have that the z's must be 0. Same exact problem, just now we're including the auxiliary variables here. So the way that we got from here to here is through this auxiliary linear program. Now you might be asking yourself, if we know that all of the z's have been zeroed out, why are we keeping them around? Okay, we know that all of the z's are 0, so why not just drop them from the problem and solve this original form of the problem? Why do we still have the z's here? Well, the answer is a little nuanced, right? Because yes, the z's have been zeroed out, but the initial basis, the initial partition that we get from solving this auxiliary linear program might have indices in it corresponding to the z variables. Okay, so just because they're zeroed out doesn't necessarily mean that they won't be part of our initial partition. Okay, so that's an important part to keep in mind. That's why we need to keep them around. Now, that doesn't mean that we need to keep all of them around, and typically simplex algorithm solvers will inspect that initial partition that you get and include only the specific components that are needed from that basis that is solved for. Okay, so that's why we still have the z's here, and that's why we're writing the problem in this form, because some of the indices corresponding to these z's might be present in that initial basis that we get. So now we're ready to return to our implementation of the simplex algorithm and finish it off with the last function here, minimize LP. So minimize LP, we're just going to do very similar to what we've done before. The only difference now is that we're introducing this z vector. So we make it a vector of ones here. So we have m ones. And then we're building this matrix. Okay, so this is just a one-line for loop that is saying for each j in B, check is j greater than or equal to 0. If it is, then that component will be 1, and it'll be -1 otherwise. So this will create a vector here, and then we're creating a diagonal matrix out of that vector. So this is exactly what we've written here to create this diagonal matrix Z. That's all we're doing in this line. Now we can set up our initial linear program, so the auxiliary linear program here, where we've just combined A and Z, right? Because that forms our A prime matrix, is what we're calling it. So it's just A and Z combined here. B is just what it was before, so B prime is just B. And then C prime is just combining n zeros with our Z, just ones here, okay? And that becomes our C prime. So we then create that linear program structure here. And now we can create our basis as well. Remember, we saw our basis was just n plus 1 to n plus m. So we're just collecting here. This collect just collects all of the values, 1 up to m, and then we're adding on n to that collection here, okay? And that just gives us n plus 1 up to n plus m. So now we can call minimize LP. Notice this is the one with the exclamation mark, not this minimize LP. So that's the distinction between those, because this one is modifying the basis. So we call it with the basis that we just found and the initial linear program that we've constructed, so this auxiliary linear program, and then we'll solve it. And this will modify the basis that we have. So now the basis that is returned, what we're doing here is we're checking, are any of the z components in B, right? So we're checking I greater than n, because that corresponds to the z components. Are any of those not 0? So are any of those not been zeroed out yet? We know that if that's true, then the problem is infeasible and we don't need to go any further. Okay, so that's what we're checking there. If that's not the case, then we're going to continue on to solve the problem that we're actually interested in, right? We've initialized the partition. Now we're ready to solve the actual problem. So we're going to build A prime prime here, where A prime prime is just the A matrix. So we're just making this matrix here. It's just the A matrix, the two identities, and then a 0 matrix here. The B prime prime is just going to combine B with a vector of zeros, and then C prime prime is similarly just combining C with a vector of zeros. So now we can build that linear program with our prime prime values here, and then we can call minimize LP on that specific linear program with the basis that was solved for here in the initialization phase. And now the solution that's returned, so that partition that's returned, we can then call get vertex on that. Remember, get vertex was the first function we saw. We're going to get the actual x vector here, and then we're going to access just the first n components because we don't actually care about the z values that are included. So we're going to return get vertex with just the first n components. And that is the solution. So we have now fully implemented both phase 1 and phase 2 of the simplex algorithm. And all of that was in roughly a little over 100 lines of code. So again, I think that's pretty powerful that we have that much power in the simplex algorithm in that small condensed amount of code. Okay, so we've saw both phase 1, the initialization, how do we find that feasible starting vertex, and then phase 2, how do we find the optimal vertex. Okay, so we saw that the simplex algorithm was built on these key concepts of vertex partitions, first order necessary conditions. That's really the key part there in that mathematical formulation, all sort of hinges on the first order necessary conditions. We also saw this idea of feasible sets and equality form. So now the last thing that we're going to talk about here is dual certificates. And dual certificates are basically a verification that the solution returned by the algorithm is actually the correct solution. So this is sort of a check that you can do of, hey, did I actually get the correct solution? Can I trust what's returned by my algorithm? What this relies on is the fact that the dual problem, so the solution to the dual problem, is actually a lower bound to the solution of the primal problem. And we'll see this in the next slide here. Okay, so If the solutions to the dual and the primal are equivalent, then we know that the primal problem, the optimal value of the primal problem, is guaranteed to be the unique optimizer because what we say here, the duality gap is 0. So this is sort of the key idea behind dual certificates, and we'll see this written out a bit more here in the next slide. So recall that we're working with this general formula of the Lagrangian. For our linear program, the Lagrangian we saw before is written like this. So the primal problem that we saw earlier is just we have minimize with respect to x and then maximize with respect to our Lagrange multipliers on the inside. The reason for this is so that we can recover that infinite step penalty. The dual problem, all that the dual problem does is just reverse the order of this maximize and minimize. The reason that the dual problem is a lower bound on the primal problem is because of the min-max inequality here that we've written. So all this says is that when we have this maximize with respect to a, minimize with respect to b of this function, that is going to be less than or equal to the reverse of that. So just reversing the order of the minimize, maximize. Well, that's exactly what we have here, where this is the primal problem and this is the dual problem. So that is why the dual problem is a lower bound on our primal problem, okay? When the optimal value of the dual problem is equal to the optimal value of the primal problem, then we say that the duality gap there is 0, okay? But this is just saying here that the dual problem is a lower bound on the primal problem, okay? So that's kind of just elaborating on what we saw in the previous slide. So now dual certificates here, we have the representation of the primal problem. So if we now want to look at the dual problem, we can just write this out in a little bit more detail. We just expand this out, substituting in the Lagrangian here. We can make some simplifications here by first just factoring this out so that we have this in terms of x. So we just factored out these components and written it now in this slightly different form. And now to simplify this, we can just return to our friends the first order necessary conditions here, applying the stationarity condition, right, which is where we took the gradient of the Lagrangian with respect to x, gives us that c minus mu minus a transpose lambda is equal to 0, okay? That comes from stationarity. And so that allows us to basically just drop this term since it's 0. We also have from this that we know mu is equal to c minus a transpose lambda, and we know from dual feasibility, mu is greater than or equal to 0. So we also have that constraint that we need to obey. So if we now rewrite this slightly here, we're going to have just lambda transpose times b. Well, notice that this doesn't depend on x at all. So we can actually remove this minimize with respect to x because x doesn't show up here. So if we remove that, we just get maximize with respect to lambda now, because mu also doesn't show up here. So we just have maximize with respect to lambda, lambda transpose b. We still, however, just because we've dropped mu here, we still have this constraint on mu, that mu equal to c minus a transpose lambda is greater than or equal to 0. Okay, so we still have that. So now writing the entire dual form of the problem out, we have the following. We have maximize beta transpose lambda with the following constraint that a transpose lambda is less than or equal to c. Okay, so comparing that to the primal problem where we had minimized c transpose x with ax equal to b, what we see here is that in the primal problem, we had n variables because x has n dimensions, and we had m constraints because A was an m by n matrix. Now in the dual form of the problem, we know that lambda is m dimensional, so it's m by 1, and then we have n constraints here because we're looking at A transpose now. So we have n constraints. So why would we ever want to do this? Well, notice that if the primal has n variables and m equality constraints, and we saw that the dual has m variables and n equality constraints, then typically what we're going to have is that m is less than or equal to n in this original problem, otherwise we'd be over-constrained. So typically we'll have fewer variables here in the dual to work with. And this means that the dual problem is usually going to be more efficient to solve. Okay, so that's one nice part of the dual problem. So that's just writing out the dual and primal problem. So you would now be able to go and solve this dual problem here. There is an alternative to the simplex algorithm called the self-dual simplex algorithm, and that actually tends to be faster in practice than the just normal simplex algorithm. And it doesn't require that A basis matrix satisfy the X basis equal A basis inverse times B greater than or equal to 0 that we saw. Okay, so that's just a little additional extra if you're interested in looking into some of the literature on the self-dual simplex algorithm. What we're interested in here is dual certificates. So imagine that you're walking down the street and someone approaches you and they say, hey, I've got an X star lambda star pair. Is it optimal? And as you can imagine, this happens very often, so you'll want to be prepared. And before watching this video, you might have said, I have no idea if your X star lambda star is optimal. Just leave me alone, please. But after watching this video, you could say, well, I can answer that. First, I'm going to ask you some questions. So I want to know, is X star, the X star that you have, is it feasible in the primal problem? And the person will say to you, yes, it is feasible in the primal problem. And you'll then say, well, how about the lambda star that you have? Is that feasible in the dual problem? And they'll say, yes, that's feasible in the dual problem. And you'll say, okay, all right, that's good. How about the P star? Is the P star value, meaning the optimal value of the primal problem, is that equal to C transpose X star? And they'll say, yes, it is. And you'll say, okay, one more question. Is B transpose times lambda star equal to your optimal value of your dual problem? And is that equal to P star? And if they say yes to that, then you can confidently say to them, yes, your X star lambda star pair, your primal dual solution pair that you have is optimal. That is the optimal pair because you have this duality gap of 0 here. And so that's what dual certificates allow us to do. They allow us to verify that a candidate primal dual solution pair is optimal. Okay, so it's a way to sort of check, is the value that I got, that I returned from my simplex algorithm, is that actually truly the optimal point? And the dual certificate allows you to verify that. Okay, so now summarizing everything that we've seen so far. We saw that these linear programs are just these linear constrained optimization problems where we have a linear objective and linear constraints. We saw that through the simplex algorithm, we were able to optimize these linear programs to global optimality in a very efficient manner. And then once we have that solution, we can check it through dual certificates, which allow us to verify whether or not a candidate primal dual solution pair is optimal. So I hope this was helpful. I hope this was useful to you. Yes, there are a lot of steps involved in the simplex algorithm, but I think that when you break it down, each step from one to the next sort of flows and it makes sense. And then when you put all of those steps together, you get something really beautiful in the simplex algorithm in not that much code. And all of it is really based on those first order necessary conditions. And so what we've seen is that these linear programs, while yes, you're sort of constrained to either be working with this linear objective and these linear constraints, if you're able to get your problem into that form, then you're in really good shape because you can solve these massive problems to global optimality extremely efficiently. And I think that's just a really powerful tool. So I hope that was helpful to you, and thank you all for listening.